Okay, so this is the title of the course, as you all might be knowing by now. So let's just try to understand first that what do we do in numerical analysis, and like why we need to study the numerical analysis first of all, right? So for that, if you observe, there are many physical phenomena which we have to formulate it as a mathematical model, right? So for example, if you have a object of mass m and it is falling under gravity, right? And if you try to model this phenomena of this falling object, then what is going to be the equation which you will get? It is going to be, so if we take v as the velocity and m is the mass of this body, so you will get it as mg minus some constant times say v square, where c is some constant. Okay, so this is nothing but the drag force because of the air resistance, right? So this is one simple example, but there are plenty of the phenomena just in the real life you can find that which when you model it, so when you have to formulate it as a mathematical model, right? So you get, so this example is simple, but we get many complex mathematical models out of the modeling of these physical phenomena. So what we are interested in solving these mathematical models, right? But most of the times these mathematical models are so complex that you cannot find their solution in the closed form. That is, you cannot solve them analytically. Okay, that's where the role of the numerical analysis comes. So we have to find, what we try to do in the numerical analysis, we try to find the approximate solutions of the exact solutions of these mathematical models, right? And we try to do the error analysis. That is, we try to analyze the error present in these numerical methods, which we will be deriving for the approximation of the mathematical models. And the most beautiful part about the numerical analysis is that all the numerical methods which you will see in this course, you can implement them in the computer or using some software, and then you can just verify all the theoretical findings using some numerical examples. Okay, so in fact, we will try our hands on some software, say MATLAB, towards the end of this course, if the time permits. But for the time being, let's start with the. So we have, say, the solution of, for example, so for example, if we have, say, V as your exact solution of the mathematical model, right? So using the numerical methods, we will be getting some approximation of this exact solution. And what we try to analyze is that how well this VH approximates the V, right? So that we will see in the error analysis, but that is one of the error which we have it in the numerical analysis. But there are many ways the error can occur in the when you're analyzing the numerical methods. So let's see that what kind of all kind of errors we can have in the numerical methods. So firstly, so you can have the error in the mathematical model itself. Meaning that when we try to model any of the physical phenomena, we put a lot of assumptions to simplify the model, right? And if you are putting a lot of assumptions, it might happen that your mathematical model, what you are getting, is not that accurate, right? And then if you're trying to find the approximation of that model, of course, you're not going to get a good approximation of the actual solution, right? So for example, in this example, if I just do not take into account this drag force, right? So simply I consider this model and then I try to find a numerical approximation of this model, right? So the solution which discrete solution or the approximate solution which we will get, that might not be a good solution of the actual solution of this complete model, right? So that is one of the reason that if your mathematical model itself is not correct, you cannot expect your numerical solution to be a good approximation of the exact solution. Okay. Secondly, you can have the error in, say, physical data. So suppose the mathematical model which we get that involves some parameters. For example, here you have the C presence here, right? And these parameters are coming through some physical measurements. That is, you're conducting some experiments, and through those experiments, you're getting the values of these parameters. So we know that the physical experiments, they involve some error, right? And if you're going to do the computations based on those parameters, of course, your numerical solution will not be that accurate, right? So this is one of the reason that that might affect the accuracy of the numerical solution. Thirdly, we can have a machine error. So as I said, that numerical methods which we will be seeing in this course, they all can be implemented in the computer, right? So this error arises because computer can store numbers only in the finite precision, right? So because computer has its own limitation, you cannot store a number which is too long. Okay, so there's a process which is called the rounding. So basically, machine error is also called the round of errors. So when the number is too long, what we do, we just round it off. And if you're already familiar with the rounding in the decimal system, right? So for example, if you have a number 2.9443214, and then if you round it off, what do we do? Suppose I'm doing the rounding. So what I will get as an output is this itself, right? So basically this last digit is just chopped off because it is strictly less than 5, right? And if you consider, say, this number 3215, then if you round it off, so of course the last digit will be chopped off, but then the previous digit will be increased by 1. Right? So such kind of rounding is required to store a the long number when the number is very long. So, and you have to store in the computer. So you will do some rounding. So that creates some round of errors. Okay. But what we are interested in this course mainly is the approximation errors. So meaning the error which is, so as I explained, suppose V is your exact solution. Considering that your model is good enough and it does not involve, it's accurate enough with all the correct parameters. So you get V as an exact solution. And then we find VH as an approximate solution by using some numerical methods. Okay. So basically, we want to analyze the approximation error, which is V minus VH. So we will be seeing it in a different norms that how this error behaves. So for all the methods which we are going to see in this course, we will be interested in the numerical approximation, but at the same time, we will also be seeing that what is the error we are committing when we are approximating it by those numerical methods. Okay, so one of the most frequently arising, the problem which arises in the applied mathematics is to find the roots of a nonlinear equation, say fx is equal to 0. So I'm just considering the one variable case. Okay, and let's take that we are looking for the solution in the interval AB. So for example, you can take, you would have come across solving quadratic equations, cubic equations, right? So let's take this example, 5x plus c. And then you have to find the root of this equation, root of this function f. So you will say that, okay, this is very easy. You can simply find it and you will get it as 2 and 3 are the roots of the f. Right? So in this case, it was very easy. But now let's change the function f. Suppose my fx is exponential x sine x, and let's take it to be minus x by 2. Okay, and then I have to, what I am interested in finding the root of f. Okay, so now you can see that it is not so evident that how will you find the root of the f in this case, right? So there are some very simple and elegant numerical methods which one can use to find the approximation of the root of this equation, or in general for any nonlinear equation. Okay, so these methods are going to be iterative methods. So we are going to basically see some of the iterative methods which can be used to approximate the roots of the nonlinear equation. Now, before going into the any particular method, let's understand what are the iterative methods. So iterative methods, what do we do? That we will start with some initial guess, say x naught, okay, and then we apply the method. So we will see the particular methods for solving these equations, and we apply the method, and upon applying, we will be generating the, say, the next iterate, x1, right? And then we use this iterate to generate the next iterate. So basically, we will be generating a sequence of the iterates. And what are the iterates in this case? This is nothing but the approximation of the root. Let's say the exact root is x star. Okay, so these x1, x2, x3, which we are going to generate using the this numerical method or the iterative method, they are all going to be the approximation of this root. And what do we expect? That this sequence of iterates, this will converge to the root of given equation. That is, it will converge to x star. So that is what we expect, that we are generating a sequence of the iterates using the numerical method, and then we expect that as a sequence, this xn should converge to x star. So here we have seen few words, the convergence, right? Convergence of the iterative method. So there's a notion associated with the convergence of the iterative methods, which is called the order. So let's try to understand that. So this is the definition. So suppose you have a sequence of iterates. Let's call it, say, xn. And we say that this converges with order p to a point x star if, so if I say the difference of xn plus 1 and x star, this should be less than equal to some constant times the error at the nth iterate raised to power p. Okay, and c here is some positive constant. Okay, so you say that the sequence of iterates xn, this converges to x star with the order p if this happens. Okay, and in particular this holds for p equal to 1 also, that is the sequence is set to converge linearly okay, there's a lot of disturbance. Okay, so we are talking about the linear convergence here. That is the case when p is equal to 1. But what we require in the case of the p is equal to 1, that c has to be strictly less than 1. Okay, so if p is equal to 1 and c is strictly less than 1, then the sequence is set to converge linearly to x star. And you will see that the c less than 1 is important, because what do we have in case of p is equal to 1? That xn plus 1 minus x star, this is less than equal to c xn minus x star. So if I just keep repeating this procedure, so I'll get this is less than equal to xn minus x star is going to be less than equal to c times xn minus 1 times x star. So I'll get c square, right? So if you use this by index, and what we will get that xn minus x star, this is less than equal to c raised to power n x naught minus x star. Okay, and your c is strictly less than 1. So this shows that xn converges to x star, right? So this is how we understand the order of convergence. So when we say that a sequence converges, but with what order is, this is what how we determine the order of the convergence. Okay, so when we talk about the linear convergence, so either you can realize this relation or it suffices to realize this relation. So both ways, if you're able to prove any of this, then you say that the sequence converges linearly to x star. Okay, so now suppose we are applying the iterative method. That is, we start generating the iterates. We start with x naught and then we found x1, x2. So one thing is that we do not expect that any of these xi's will exactly coincide with x star, right? We are not really expecting to produce the exact solution x star, right? What then question arises that where do we stop? We have to stop somewhere, right? We cannot go on forever computing x3, x4, and then x100. We have to stop at some point, right? So what has to be the stopping criteria? Where should we stop, right? When do we feel that, like, it should be something like we feel that we have got a good approximation of the x star, right? Then we should stop. So let's just see some stopping criteria to truncate these iterations. So the following criteria we can use. So let's see the first one, which is based on absolute error. Okay, before that, I should explain what do we understand by the absolute error. So we have a approximation and we have an exact solution, right? So we are calling the approximation by x. Let x be the approximation of x star. Then of course, as it says itself, right, absolute, you're just computing the absolute value, absolute error. So the error is nothing but x minus x star and absolute value of this. So this is called the absolute error. Absolute error in x. Okay. And there's a notion called the relative error. So for this, so again, by the name, you can understand that this is a relative error. So this means that I'm having the division by the absolute value of the x star. But here you can see that I have to assume that x star is not close to 0, not equal to 0. Okay. So these errors can be used in to stop the iterative algorithm. So we'll see how. Now, one more point I would like to put here, that these relative errors, these are more significant. So let me just write it. So these are usually more significant than significant measure. Than the absolute error. Okay, so see, first of all, you can observe that if your x star is close to 0, then of course your relative errors are not going to be meaningful. Okay, but if your x star is not close to 0, and another case, let's take when your x star is close to 1. It's close to 1, then of course you can expect that relative error and the absolute error there'll be not much difference between both of them. Okay. So in this case, what will happen? There's not much difference between absolute and relative errors. Okay, but if your x star is greater than 1, then of course your relative errors, they are going to be more significant than the absolute error. So let's try to take one example. So suppose I have my x star to be, so let's take the value 1, and as an approximation, say I get it 0.99. Okay, so let's take few values here, 1, and then say 1.01, and let's take 100, and then say I get 19.99, 99.99, and as an approximation, let's say I get 99. So you can try to compute the absolute error in x and also the relative error. Okay, so you can simply take a difference and that will give you the absolute value here. So I'm just going to write the numbers here. So this will give you 0.01, 0.01, and this is also going to give you 0.01, and here you will get 1, right? And the relative error, if you try to compute for the same x and x star, you will get it as 0.01. 0.01. Of course, you see that x star is close to 1 in these two cases, right? So your absolute error and the relative error, they both are going to be same. So it's exactly 1 in this case. And in this case, if you will compute, you will get it this. And in this case, it is going to be this, right? So you can see that when your x star is large, right? So in that case, your absolute error becomes very large, right? So suppose you are trying to put say you are looking for that your error should go down by say by tolerance 10 to the power minus 5, and if you can compare that you have here 10 to the power minus 2 and this is 1, right? So if you're setting the stopping criteria using absolute error, you have to use a lot of iterations to reach up to the tolerance whichever you'll be setting in the algorithms. Okay, so the relative error is most of the time is a good measure for the stop like the tolerance when we will set. So we will use the relative error to stop the algorithms. Okay, now let's see how can we use these errors as a stopping criteria. So as we see that we are generating a sequence of the iterates, right? So starting from say x0, we found x1, and then we are finding x2 and likewise, right? So the question is that where we want to stop. There has to be some step where we have to stop, right? So how can we check that like what are the conditions we can put to stop the algorithms? So the first condition you can put is based on the absolute error. That is, suppose you already have the xn minus 1 and using this you computed the xn. Okay, so I'm going to check the difference. That is, this is absolute value and you have already set some tolerance. Suppose you want that error should be less than some, this tolerance is given by the user. So say you can say that I want the accuracy up to 10 to power minus 9 or 10 to power minus 8. So this is up to you that how accurate you want. Okay, so this is one way. So and or you can use the other way to stop the algorithm, which is based on the relative error. So I'm going to compute this quantity, okay, and I will check that whether this is less than my set tolerance. So this tolerance is again in my hand, so let me call it epsilon 2, okay, and if your xn is satisfying this condition, then of course you will the algorithm will be stopped. Okay, so here let me write that epsilon 1 and epsilon 2, these are user defined constants. Okay, so now let's see one particular method and then we'll see all these things which we have understood here, that how can we relate to that. So the first method to find the approximate roots of this equation is bisection method. So let me give it a equation number. So say this is 1. And you will see why do we call it as a bisection as I will explain the method. So first of all, this method is based on the intermediate value theorem. So let's recall what is the intermediate value theorem. So can any one of you tell me the statement of the intermediate value theorem? Okay, I'm writing, maybe you can help me to complete it. So let me take a continuous function from the interval AB to R. Okay, and if we have say some D, which is in the interval FA, FV, or in fact you can have a closed interval, open interval. Either way, closed or open, depending on that, you have to change the okay, so let me take a closed interval. Then there exists
constant C.
Yeah.
Constant
Equal to D.
F equal to D.
Right. So basically, if f is continuous, it will take all the values in this interval AB, right? So there exists say some C, which is in the interval AB, such that
F equals
to D.
right. So this is what the intermediate value theorem says, that right. So if you consider any point between FA and FV, you will find some C in the interval AB, which will attain this value D, right? So the bisection method is basically based on this theorem. Now let's see, just try to see that what happens if I take, suppose I choose the 2 points A and B such that the function changes sign between A and B, right? Meaning, so I have
the 0 between A and B.
exactly. So as a consequence of this initial value theorem, you will have that there will exist a point where the function will be 0, right? So suppose f at A is negative and f at B is positive, right? So we know that there's a between, because f is a continuous function, so there will be a point where it will be taking a value 0, right? So f changes sign between A and B, then as a consequence of the initial value theorem, what we have, so I'm stating this as a theorem again. So we have f A and B such that the f has a different sign at A and B. That means if I consider this product, this will be strictly less than 0, right? And we assume that f is a real valued continuous function. Then there is at least one root of f between A and B. Right? You all agree with this? That
Yes, ma'am.
so this is my function fx. So if f has a different signs at A and B, that is it changes the sign in the interval AB, then of course there will be one root which will be lying in this interval AB. Okay, so let's try to get more insight about this theorem by taking some examples. So I'm just trying to use some pictures here. So let me just draw some function. Okay, and let me take, so suppose this is my function fx. And let me take 2 points A and B. So I'm going to take my A here and I'm going to take my B here. Okay, so you can see in this graph, FA is also positive, FB is also positive, but you see that there lies two roots between the interval AB, in the interval AB. Two roots between A and B. Okay, so what is this theorem says? That this theorem just says that it is giving you a sufficient condition. Okay, so this is not a necessary condition that if there lies two roots between A and B, then FA into FB has to be strictly less than 0. Okay, so this theorem is just giving you a sufficient condition. It's not a necessary condition. So you can see in this example that you have 2 points A and B. Between them, you have the two roots, but still F and FB is strictly positive. Okay, so I just want to emphasize here that this is just a sufficient condition. Now let's take one more example. So let me write here, this is just a sufficient condition. Suppose I take my function y is equal to fx in this way. Okay, so I'm going to take my A here and B here. And this is a graph of y is equal to fx. So again, we have that in this case, we have fa is positive and fv is negative. So of course, the function changes the sign between a and b. But how many roots we have in this interval ab? So we have 1, 2, and 3. So why I'm giving this example is that this theorem just tells you that there exists one root, right? This does not quantify that how many roots are going to exist there. There might be one root or there might be 10 roots. Okay, so it is not going to give you the unique, it's not going to give you that there's exist a unique root in that interval. So it just ensuring that there exists at least one root in this interval AB. There might be more than one also. Okay, as we can see in this example. All right, and let's take one more example. So I want to take my function f as so this is okay, and let's take this is the point A and this is a point B. So you see that at A the function is positive and at B the function is negative, but there's no root between A and B. Why? Is this theorem getting hold here?
Ma'am, it is not continuous.
It is not continuous, right? So this theorem is valid only for the continuous function. Okay, so if the function is not continuous, you cannot ensure that there's going to be a one root between A and B if the function changes sign. All right. So now let me just describe the algorithm of the bisection method. That is all the steps that how you are going to find the approximation of the roots using the bisection method. Or you can say all the steps which you will be using in the bisection method. So again, I'm going to have a continuous function. On the interval AB. Okay, and A and B and these points I'm choosing such that the function changes sign in this interval, that is fa and f is strictly less than 0. Okay, so the step one is that we have to choose A and B as an initial guess such that fa and fb, the product of this is strictly less than 0. That is basically what we are doing by requiring this condition is that we are basically bracketing the root. Okay, now let's take a figure and then I'll explain there and then simultaneously I'll write the steps. So let me take so this is my function f and I'm going to take my points A and B here. Okay, so what is the next step in this algorithm is that once we have found the points A and B such that function changes sign, I'm just going to find the midpoint of this interval. So which is going to be A plus B by 2. So the step 2 is to find the midpoint. Now what are the possibilities of the values of the f at m? So what can happen?
Positive, negative, and 0.
Positive, negative, 0.
Right. So there are only three possibilities, that the evaluation of the function at m can be 0, or it can be positive, or it can be negative, right? So if f at m is equal to 0, then eventually we have got the root, right? So this, in this case, if f at m is equal to 0, this means that we have found the exact root, right? Now, if what happens if f at m is positive? So let's try to see first this case. So here, this is my FA, FB, and f at m is less than 0, right? So what I will do, I will choose my m as a. That is, my new interval is going to be MB in this case. So I started with the interval AB. So basically, I'm going to replace my A by M, and I'm going to apply the further steps in the interval MB, which is again halving the interval. That is, I will take this as my new interval AB, okay? And again, I will find its midpoint. So which is going to be somewhere here, say M2, okay? So let's call it M1, M2. Okay, and again, I will check the sign of the function at M2. And if it is positive or negative, again, the similar cases will arise. If it is 0, then of course we have found the real root. And if it is not 0, then it is going to have a sign. And then based on the sign, if it is positive, then we will take a interval to be this. That is, I will replace my B by M2. Okay. And if it is negative, then my interval will be this. Okay. So by doing this, you can see that we are reaching closer to the point which is basically the root of the function, right? So let's write down all the steps here. So if it is greater than 0, what we will do? We will be, so fm is positive, and again I have to bracket the root, right? I need that interval where the function will change the sign, because I know that my root will lie there. So I will replace my b by m, and my a will remain a, right? That is, my interval is going to be am in this case. And if it is negative, I know that I have to again bracket the root. So I have to keep my b as b, and I have to take my a as m. Okay. So when you have, now how do we check this? So I'm simply going to check the product of FA and FM. So if this is less than 0, this means that FM is positive, right? Because FA is already negative. So this is going to be less than 0. This means that the evaluation of F at M is positive. So I will replace B by M. Okay. Otherwise, that is, if FA into FM is greater than equal to 0, equal to 0 case is already done. So let's not include that here. So if this is strictly positive, so we know that in this case, FA was already negative. If the product with FM is strictly positive, this means that FM is going to be also negative. So I will replace my A by M, and B will remain as B. Okay. So basically, based on the sign of the F at M, either we will choose this as a new interval or this as a new interval. Okay. And then we will repeat the same procedure. So the next step will be that we have to again find so this is step 3. And then step 4 is going to be to find the midpoint of the new interval. And let's call it as M new. Okay. And simultaneously, we will compute the error also. So I'm just going to use the relative error. So M new minus M divided by M. And let's M new. And let's call it as error. So I'm just denoting it by ER. So in the next step, what we will do? So if, as I said, just imagine that you're going to run this algorithm. So you have to stop it somewhere, right? So I'm going to set some tolerance that say my tolerance, say epsilon, or I'm just simply going to call it as TOL as a tolerance. So if my error, this error which I've computed here, if this is less than tolerance, which is a prescribed value, then stop this algorithm. Other go to, you have to repeat the same procedure. You have to again find the F evaluation of M, and then you have to again check the sign, and you have to repeat this same algorithm. So you have to go to the step 3. Okay, so is the algorithm part clear, that what do we do in the bisection method? So we start with 2 points A and B, where the function changes. So this A and B are such that the function changes sign in this interval AB. And then each time we find the midpoint and try to check the sign. Okay, and based on the sign of the F at the midpoint, we try to choose the correct interval where the root lies. Okay.
Ma'am, what is tolerance here?
Tolerance, this is, say you are setting that tolerance maybe say 10 to power minus 5. This is some number given by you. Okay, you say you want to say that I just say I'm not interested in reaching to the exact solution. Okay, I just want that my two numbers, say if you're telling that M and M new, they are very close, this means that when you're going from one interval to the another interval, it's not, midpoint is not changing, right? So you are basically saying that I'm happy with that if I reach, say my two consecutive solutions, they are not much different. Means that even if you apply further, it is not going to change much, right? So if it reaches to say till the error is say of this order 10 to power minus 5, I'm happy with my solution. Okay, or you can say that, okay, if you want more accurate, you can make it 10 to power minus 9. So this is up to the user how accurate you want it. Okay.
Okay, ma'am.
All right, so now coming on to that, how the error is reducing. What is the error basically? Okay, first of all, let's try to understand that, say we started with the interval AB. Okay, so in the next step, if in this figure, if I see my next interval became MB, right? So it was A plus B by 2B. Right? And then you will repeat further. So what do you observe in this process? That you are, each time when you're choosing this M, you're basically halving the length of the interval. Right? So you reduce the length of the interval by half when you go from one iteration to the another iteration. Isn't it? So after the n iteration, suppose we are in the interval. So let me write it, call the interval a and b in itself. So after the n iterations, we would be in the interval, say a and bn. Okay, so how does this a and bn relates to the actual a and b? So the length of this interval is going to be, can you tell me what it will be?
B minus
A by 2 n
2 raised to power?
By 2 to the power n.
Okay, so it depends whether you are calling this as your a1 b1 or you're calling this as your a1 b1. It depends on whether you'll get 2 to power n minus 1 or 2 to power n, right? So if I call my starting interval itself as a1 b1, so after the nth iteration I will get this as my a and bn, the length of the interval, isn't it? Okay, and what will be the approximation of the roots, which is nothing but the midpoint? So xn is going to be an plus bn by 2, right? So basically we'll have this picture. So we have an, bn, and xn is nothing but the midpoint of an and bn, and x star will lie in any of the interval. Either it will lie this side or that side. So x star is the actual root. So it will be lying in one of the one side of the interval, right? So we can also see what is going to be the distance between the xn and x star. That is the error, absolute error. So you can see that this is always going to be less than equal to the half of the length of this interval, right? Which is basically b minus 8 divided by 2 raised to power n. Okay. So you can see that as n will tends to infinity, so this your xn, the sequence of the trace, this is going to converge to the x star, right? So the convergence is guaranteed here. Moreover, what we were talking about here is the tolerance, right? So suppose you have some given tolerance. You have epsilon, which is a given tolerance by the user. So we can determine that how many iterations it will take to reach this tolerance. Okay. So let me write it in this way. So if you require to satisfy further mod x star minus xn is less than epsilon for a given tolerance epsilon greater than 0. So we can determine the number of iterations n which is needed to reach this tolerance. Okay. And that we can do by simply demanding that what is my error we have got here is that b minus a divided by 2 raised to power n. This would be less than epsilon. So I'm going to find my n such that this quantity is less than epsilon. So this basically gives that if you simplify this, this is going to give you that n should be greater than okay. So basically, what are the minimum number of iterations required to achieve the accuracy epsilon, that is nothing but, so I'm just going to take this as a minimum number. If this is an integer, and if it is not an integer, I will take the next, the positive integer, right? Say suppose this is coming to be say 10.1, right? Then I'll just take 11 as the number of iterations. So this is given by, so let me just right. So this is the minimum number of iterations which will be required if you want to set the tolerance, say whatever the tolerance you set, based on that you can determine that how many iterations you will be required to reach this tolerance. Okay, so let's understand it by taking some example. So let me just take the length of the interval. So let the length of the interval is 1. Okay, and we have to find out the minimum number of iterations required to achieve an accuracy of, say, let me give two values. Say epsilon is equal to 0.01. So one I will do, and one you can take it as an exercise. And then epsilon is equal to 0.001. Okay, so let me do it for epsilon is equal to 0.01. So we already know the length of the interval, b minus a is 1, and we know we have already derived that what we have to evaluate to get the minimum number of iterations. So we know that n has to be greater than, or even you could have started with the, sorry, so you can have the greater than equality, so that you can have, I'm taking that as the minimum number of iteration, right? The last value. So here the n has to be greater than equal to log of b minus a is 1 divided by epsilon divided by log of 2. So base here is e in the log. So you can simplify this and you will get it as 6.6. Okay, but the number of iterations has to be an integer, right? It cannot be a fractional. So what are the minimum number of iterations?
7.
लिस्ट इंटीजर फंक्शन लगा दो.
Number of iterations
7.
is going to be 7. Okay, so it just depends. The higher tolerance you will set, you will require a more number of iterations, right? But of course, you have to realize that the higher tolerance meaning you are reaching much closer to the exact solution. Okay, now let's take one more example just to see that how does this bisection method works. So you have to find, okay, I just need to check the battery of my, okay, it's fine. So we have to find a root of, so I'm taking a simple equation, x squared minus x minus 3, this is equal to 0. So whose root you can find it by using the standard method, which you know, but we are going to apply the bisection method and see what we get out of it. And you have to find the root which is correct up to at least 3 decimal places. Okay, so here again, I have to choose 2 values a and b such that the f will change the sign in the interval ab. Right? So you can check it that if we take a is equal to 1 and b is equal to 3, that is, you can check that f1 is nothing but -3 and f3 is nothing but 3. So we have an interval where the function changes the sign. Okay, so my interval is going to be 1, 3. So this is my initial guess. And I'm going to set my tolerance.
B equals to 2.
Sorry?
2 and 3.
Sorry, ma'am, no.
Is it correct? Okay, you can
2
check
and
that.
3 will work, ma'am.
And 2 and 3. A is
Ma'am, 2 will also work for a equal to 2.
Okay, so see, they're not a unique choice. You can take any choice. So for example, for 1 also worked, 2 can also work. So you can choose an interval where the root will lie. Okay, so the A and B are not unique here. All right. So for example, I have chosen 1 and 3. You can find 2 other values which will give you that the function changes sign there. So I'm just trying to explain that how will you apply this method. All right. So these values are correct, right? If I take 1, we get -3, okay, and then if I take 3, 9, 6, -3, yeah, so this is correct. Okay, so I'm going to set my tolerance to be 10 to the power -3 because I need that accuracy at least. So now I have to apply this, find the midpoint and then check the sign. So I'm just going to form a table, okay, rather than doing it so let me just take the values of the A and B. So let me call it AN and BN. And I will get the corresponding midpoint, and then I will check the function value at that midpoint, and then you can find the error also. So error meaning you can just take a either relative error or the absolute error. So let me, for the simplification, I'm just taking the absolute error, and here I can take a number of iterations. Okay, so initially I've got n a1 as 1 and b1 as 3, and x1 is going to be 2, and f at x1 is -1. So this is the iteration 0, and you can find the error here. Okay, so once you have got now I know the sign of the f at the midpoint, it is negative, right? So I know that f at a is negative, so I'm going to replace, this is going to be my m, and this will remain as it is, right? Again, I will find the midpoint and I will evaluate the function value at this midpoint. So this is going to be 0. You can compute it. I already have this number. What is it? 0.75. Okay, and you can find the error also here. So likewise, you can repeat till the time you reach the desired accuracy. Okay. So this, I'm leaving it further. I'm just trying to tell that how will you compute it. Okay, I hope the idea is clear here. So now let's see. Let's just summarize that what are the advantages we see for this bisection method. And let's try to argue if there are any further disadvantages also for this method. So first of all, let's focus on the advantages of this method. So the first and very important advantage of this method is that it is always convergent. That is a sequence which is going to come out out of this bisection method that will always converge to the exact root. Okay. Because what we are doing, we are taking an interval where the root lies, right? And each time we are halving the interval so that, and then we are choosing the interval so that after the halving, we are choosing that interval where the root lies. And again, we are halving it. So we are, by doing this process, we are reaching closer and closer to the exact solution, right? So what is going to be the error? We have already seen that the error bound of nth iteration is, so if I denote the error at the nth iteration, that is mod x star minus xn by en. So this we have seen that this is of given by this, right? So what will be the en plus 1? So en plus 1 will be 2 raised to power n plus 1. And in terms of the en, this is going to be en by 2, right?
Yes, ma'am.
So what does this say is actually? In terms of the convergence, can you say something? We have seen we have seen a definition of the convergence of the iterative methods, right? So can you relate this to something like that? So can you say that error converges with the linearly, quadratically? What is the order of
Ordered one.
The model is 1.
This is a linear convergence, right? So here
Yes.
the error converges linearly. And this C which we were talking, okay, I did not mention it there. The C which we had in the definition of the convergence. Yeah, in the linear convergence. So this C is called the rate of convergence. Okay, so which is 1 by 2 here. Okay, so the method is always convergent. So that is a one very important benefit of this method. And the secondly, you can see that the error can always be controlled, right? So the error is always, so you set, meaning the desired accuracy, and you will be able to reach that desired accuracy within the finite number of iterations, right? Which we have already seen that we can find the n for which we will be able to reach that epsilon. Okay, but at the same time, when we derive this relation between that how the error reduces from one iteration to another, we could realize that this is just reducing with the linear rate. That is, if you go, you have some certain error at one iteration, when you go to the next iteration, it is just going to get halved. Okay, now imagine you start with a very large interval AB. Okay, so it will take a, and if you choose your, say, one of the point A or B very near to the root, okay, then it will take a very large number of iterations to actually converge to the actual root. Okay, so this is going to be a disadvantage of this method. That it's a slow convergence. The convergence is very slow. The linear convergence meaning at each step you're just halving the error. That's all. And this is the main drawback of this method. Okay, and the other drawback is that there exist the functions for which you cannot find the root using this method. For example, if I take the function y is equal to x square, we know that x is equal to 0 is the root of x square equal to 0, right? But you cannot find the a and b so that the function will change the sign. So you cannot apply the bisection method to find the roots of this x square equal to 0. Okay, so the next thing in this direction will be that, okay, we could realize that the main drawback of this method is that this is a slow convergence method. The convergence is just linear. So we will be seeing the method which will converge with the higher rate than this method. Okay, so we are going to stop here. If you have any questions, you can ask. Okay, and kindly let me know the timing of the for the tutorial, if possible by today or at max by tomorrow. Is that okay?
Okay, ma'am.
All right, so in case there are no questions, we'll stop here.
रेफरेंस बुक्स बता दीजिए प्लीज.
Yeah, I'll send that information sheet to you all, okay?
ओके, थैंक यू.
All right, thank you.
Thank you, ma'am.
Thank you.